Hello, everyone. My name is Tom Gajinski, and welcome to my presentation for the VCCA 2025. In this presentation, I will talk adversarial training for efficient end-to-end speech denoising in cochlear implants. A cochlear implant, or CI for short, is a surgically implanted medical device that can restore hearing to a profoundly deaf person. The sound is captured by a microphone located in the speech processor, which will use an algorithm called the sound coding strategy to transform the time domain signal into a frequency domain electrical pulses that will be sent to the emitting coil located fixated magnetically on the head of the subject, received by the receiving coil implanted to the skull of the subject, and sent to an electrode array implanted inside the cochlea, where the auditory nerve will be stimulated. In this talk, mainly we will focus on what happens here in the speech processor. So the sound coding strategy, as I said, is the algorithm in charge of transforming the time domain signal into the electrical pulses that will stimulate the auditory nerve. There are different sound coding strategies out there in the market, but we will focus on the ACE sound coding strategy, or Advanced Combination Encoder. The block diagram is shown in this slide here. It's comprised first of an FFT that converts the time domain signal into a 65-bin spectral representation of it. The envelope detection block that will group the 65 bins into 22 bands. The band selection will select n spectral maxima. The LGF, or loudness growth function, will compress the selected bands between 0 and 1. And finally, the mapping will map the stimulation amplitudes to each electrode between its threshold and comfortable levels. Finally, we can represent graphically the stimulation patterns using an electrodogram. Current CI technology provides good open-set speech understanding in the majority of patients. Children can achieve a near-to-normal speech and language development if implanted early enough. These benefits, however, are greatly reduced with background noise. However, front-end speech enhancement algorithms can be used to remove interfering background noise and recover speech intelligibility in CI users. In this work, we propose an end-to-end speech denoising strategy that replaces most of the ACE processing with a neural network, as shown in the block diagram. This approach is designed to code incoming sound and perform speech denoising. And as you can see in the block diagram, we have input audio, a DNN module, a deep neural network, and then a band selection and mapping blocks that are left the same way as an ACE because they're highly subject dependent. And the idea of the sound coding strategy is to remove the noise present in the incoming signal and provide with the clean electrodograms. Here we investigate three models that we propose, and we call this deep ACE. The first one is comprised of an encoder, a separator, a deep envelope detector, and finally a decoder. In B, we have a similar architecture. However, the deep envelope detector is applied after masking, after the masking operation. This provides a high resolution time frequency masking and potentially better speech denoising. And finally, we take the B architecture and couple it with a discriminator, such as an GAN network. So here we are using adversarial learning to create more realistic electrodograms. Here, the idea is that the discriminator will try to discriminate between generated and clean electrodograms from the data set we're using. This, at inference time, will keep the number of parameters the same as in B, but we aim at improving the electrodogram generation. Here in this slide, I just show or point out the main differences between the ACE sound coding strategy, the clinical sound coding strategy, and deep ACE. As you can see, the DNN module and deep ACE will estimate the clean LGF outputs, let's say. Then these will be fed into the band selection and finally to the mapping. We use 10 hours of speech signals from the LibriVox corpus mixed with a demand dataset, which are noises found in nature or in daily life objects such as washing machines and stuff like that. The validation will be 2 hours, so it's like basically 20% of the training set. The testing will use German dataset, the HSM sentence set. And then also for testing, we have noise conditions such as CCITT, stationary noise, and ECRA7, which is 7-speaker babble noise. The SNR ranges we're using for testing and training range from -5 to 10 dB. And yeah, these are the results. This is the SNR improvement we obtained with a different algorithm using also the TASNet and adversarial TASNet as baselines. And we show this for two different noise types, the CCITT and the ECRA7 noises. In both noise conditions, the adversarial D-Pace outperforms the rest of the baselines, but also the other D-Pace models. The LCCs, the linear cross correlations, which indicate how the estimated electrodograms are correlated to the actual clean speech, the target ground truth clean speech. And this cross correlation is shown as a function of the electrode for the two different noise types. And as you can see at lower frequencies, these LCCs tend to go lower because there's where more noise is present, and they tend to go a bit higher when close to the more high frequency electrodes. In general, adversarial D-Pace is higher than the other ones, for the exception of the high frequencies. So it performs more realistic or better noise reduction at lower frequencies than the baseline models. So here in this work, we present an adversarial learning paradigm, and we observe that it actually boosts and improves noise reduction compared to the baselines. Also, we observe that repositioning the deep envelope detector and performing higher resolution time frequency masking improves noise reduction compared to the previous D-Pace model. This performance improvement compared to the time domain end-to-end baseline speech noising system like the TASNet is because the electrodograms are simpler to predict and they contain less information or more redundancy. And this is the reason we think we observe these improvements. We also observe improvement in SNR and LCC metrics. And future work will focus on further optimization of these paradigms. Thank you for your attention, and I'll be open for any questions you may have. Thank you very much. I didn't.